The Lockheed Martin F-35 Lightning II is an American family of single-seat, single-engine, all-weather stealth multi-role combat aircraft that is intended to perform both air superiority and strike missions. It is also able to provide electronic warfare and intelligence, surveillance, and reconnaissance capabilities. Lockheed Martin is the prime F-35 contractor, with principal partners Northrop Grumman and B Systems. The aircraft has three main variants: the conventional takeoff and landing F-35A, the short takeoff and vertical landing F-35B, and the carrier-based F-35C. The aircraft descends from the Lockheed Martin X-35, which in 2001 beat the Boeing X-32 to win the Joint Strike Fighter program. Its development is principally funded by the United States, with additional funding from program partner countries from NATO and close U.S. allies, including the United Kingdom, Australia, Canada, Italy, Norway, Denmark, the Netherlands, and formerly Turkey. Several other countries have also ordered, or are considering ordering, the aircraft. The program has drawn much scrutiny and criticism for its unprecedented size, complexity, ballooning costs, and much delayed deliveries. The acquisition strategy of concurrent production of the aircraft while it was still in development and testing led to expensive design changes and retrofits. The F-35 first flew in 2006 and entered service with the U.S. Marine Corps F-35B in July 2015, followed by the U.S. Air Force F-35A in August 2016 and the U.S. Navy F-35C in February 2019. The aircraft was first used in combat in 2018 by the Israeli Air Force. The U.S. plans to buy 2,456 F-35s through 2044, which will represent the bulk of the crewed tactical aviation of the U.S. Air Force, Navy, and Marine Corps for several decades. The aircraft is planned to be a cornerstone of NATO and U.S. allied air power and to operate until 2070. Development. Program origins. The F-35 was the product of the Joint Strike Fighter program, which was the merger of various combat aircraft programs from the 1980s and 1990s. One progenitor program was the Defense Advanced Research Projects Agency Advanced Short Takeoff/Vertical Landing, which ran from 1983 to 1994. Astaflow aimed to develop a Harrier jump jet replacement for the U.S. Marine Corps and the UK Royal Navy. Under one of Astaflow's classified programs, the Supersonic Staflow Fighter, Lockheed Skunk Works conducted research for a stealthy supersonic Staflow fighter intended for both U.S. Air Force and USMC. A key technology explored was the shaft-driven lift fan system. Lockheed's concept was a single-engine Canard Delta aircraft weighing about 24,000 pounds empty. Astaflow was rechristened as the Common Affordable Lightweight Fighter in 1993 and involved Lockheed, McDonnell Douglas, and Boeing. In 1993, the Joint Advanced Strike Technology Program emerged following the cancellation of the U.S. Air Force multirole fighter and U.S. Navy's Advanced Fighter Attack programs. MRF, a program for a relatively affordable F-16 replacement, was scaled back and delayed due to post-Cold War defense posture easing F-16 fleet usage and thus extending its service life, as well as increasing budget pressure from the F-22 Advanced Tactical Fighter program. The A/FX, initially known as the Advanced Attack, began in 1991 as the USN's follow-on to the Advanced Tactical Aircraft program for an A-6 replacement. The ATA's resulting A-12 Avenger II had been cancelled due to technical problems and cost overruns in 1991. In the same year, the termination of the Naval Advanced Tactical Fighter, a naval development of U.S. Air Force ATF program to replace the F-14, resulted in additional fighter capability being added to AX, which was then renamed A/FX amid increased budget pressure. The Department of Defense's bottom-up review in September 1993 announced MRFs and A/FX's cancellations, with applicable experience brought to the emerging JAST program. JAST was not meant to develop a new aircraft, but rather to develop requirements, mature technologies, and demonstrate concepts for advanced strike warfare. As JAST progressed, the need for concept demonstrator aircraft by 1996 emerged, which would coincide with the full-scale flight demonstrator phase of ASTOFLOW/CAF. Because the ASTOFLOW/CAF concept appeared to align with the JAST charter, the two programs were eventually merged in 1994 under the JAST name, with the program now serving the U.S. Air Force, USMC, and USN. JAST was subsequently renamed to Joint Strike Fighter in 1995, with STOFLOW submissions by McDonnell Douglas, Northrop Grumman, Lockheed Martin, and Boeing. The JSF was expected to eventually replace large numbers of multirole and strike fighters in the inventories of the U.S. and its allies, including the Harrier, F-16, F/A-18, A-10, and F-117. International participation is a key aspect of the JSF program, starting with United Kingdom participation in the ASTOFLOW program. Many international partners requiring modernization of their air forces were interested in the JSF. The United Kingdom joined JAST/JSF as a founding member in 1995 and thus became the only Tier 1 partner of the JSF program. Italy, the Netherlands, Denmark, Norway, Canada, Australia, and Turkey joined the program during the concept demonstration phase, with Italy and the Netherlands being Tier 2 partners and the rest Tier 3. Consequently, the aircraft was developed in cooperation with international partners and available for export. JSF competition. Boeing and Lockheed Martin were selected in early 1997 for CDP, with their concept demonstrator aircraft designated X-32 and X-35 respectively. The McDonnell Douglas team was eliminated and Northrop Grumman and British Aerospace joined the Lockheed Martin team. Each firm would produce two prototype air vehicles to demonstrate conventional takeoff and landing, carrier takeoff and landing, and STOFLOW. Lockheed Martin's design would make use of the work on the SDLF system conducted under the ASTOFLOW/CAF program. The key aspect of the X-35 that enabled STOFLOW operation, the SDLF system consists of the lift fan in the forward center fuselage that could be activated by engaging a clutch that connects the drive shaft to the turbines and thus augmenting the thrust from the engine's swivel nozzle. Research from prior aircraft incorporating similar systems, such as the Convair Model 200, Rockwell XFV-12, and Yakovlev Yak-141, were also taken into consideration. By contrast, Boeing's X-32 employed direct lift system that the augmented turbofan would be reconfigured to when engaging in STOFLOW operation. Lockheed Martin's commonality strategy was to replace the STOFLOW variant's SDLF with a fuel tank and the aft swivel nozzle with a two-dimensional thrust vectoring nozzle for the CTOL variant. This would enable identical aerodynamic configuration for the STOFLOW and CTOL variants, while the CV variant would have an enlarged wing to reduce landing speed for carrier recovery. Due to aerodynamic characteristics and carrier recovery requirements from the JAST merger, the design configuration settled on a conventional tail compared to the canard delta design from the ASTOFLOW/CAF. Notably, the conventional tail configuration offers much lower risk for carrier recovery compared to the ASTOFLOW/CAF canard configuration, which was designed without carrier compatibility in mind. This enabled greater commonality between all three variants, as the commonality goal was important at this design stage. Lockheed Martin's prototypes would consist of the X-35A for demonstrating CTOL before converting it to the X-35B for STOFLOW demonstration and the larger winged X-35C for CV compatibility demonstration. The X-35A first flew on October 24, 2000 and conducted flight tests for subsonic and supersonic flying qualities, handling, range, and maneuver performance. After 28 flights, the aircraft was then converted into the X-35B for STOFLOW testing, with key changes including the addition of the SDLF, the three-bearing swivel module, and roll control ducts. The X-35B would successfully demonstrate the SDLF system by performing stable hover, vertical landing, and short takeoff in less than 500 feet. The X-35C first flew on December 16, 2000 and conducted field landing carrier practice tests. On October 26, 2001, Lockheed Martin was declared the winner and was awarded the System Development and Demonstration Contract. Pratt & Whitney was separately awarded a development contract for the F-135 engine for the JSF. The F-35 designation, which was out of sequence with standard DOD numbering, was allegedly determined on the spot by Program Manager Major General Mike Hoff. This came as a surprise even to Lockheed Martin, which had expected the F-24 designation for the JSF. Design and production. As the JSF program moved into the system development and demonstration phase, the X-35 demonstrator design was modified to create the F-35 combat aircraft. The forward fuselage was lengthened by 5 inches to make room for mission avionics, while the horizontal stabilizers were moved 2 inches aft to retain balance and control. The diverterless supersonic inlet changed from a 4-sided to a 3-sided cowl shape and was moved 30 inches aft. The fuselage section was fuller, the top surface raised by 1 inch along the center line to accommodate weapons bays. Following the designation of the X-35 prototypes, the 3 variants were designated F-35A, F-35B, and F-35C. Prime contractor Lockheed Martin performs overall systems integration and final assembly and checkout, while Northrop Grumman and B Systems supply components for mission systems and airframe. Adding the systems of a fighter aircraft added weight. The F-35B gained the most, largely due to a 2003 decision to enlarge the weapons base for commonality between variants. The total weight growth was reportedly up to 2,200 pounds, over 8%, causing all STOFLOW key performance parameter thresholds to be missed. In December 2003, the STOFLOW weight attack team was formed to reduce the weight increase. Changes included thinned airframe members, smaller weapons bays and vertical stabilizers, less thrust fed to the roll post outlets, and redesigning the wing mate joint, electrical elements, and the airframe immediately aft of the cockpit. The inlet was also revised to accommodate more powerful, greater mass flow engines. Many changes from the SWAT effort were applied to all 3 variants for commonality. By September 2004, these efforts had reduced the F-35B's weight by over 3,000 pounds, while the F-35A and F-35C were reduced in weight by 2,400 pounds and 1,900 pounds respectively. The weight reduction work cost $6.2 billion and caused an 18-month delay. The first F-35A, designated AA-1, was rolled out in Fort Worth, Texas, on February 19, 2006 and first flew on December 15, 2006. In 2006, the F-35 was given the name Lightning II after the Lockheed P-38 Lightning of World War II. Some U.S. Air Force pilots have nicknamed the aircraft Panther instead. The aircraft's software was developed as 6 releases, or blocks, for SDD. The first 2 blocks, 1A and 1B, readied the F-35 for initial pilot training and multi-level security. Block 2A improved the training capabilities, while 2B was the first combat-ready release planned for the USMC's initial operating capability. Block 3I retains the capabilities of 2B while having new hardware and was planned for the U.S. Air Force IOC. The final release for SDD, Block 3F, would have full flight envelope and all baseline combat capabilities. Alongside software releases, each block also incorporates avionics hardware updates and air vehicle improvements from flight and structural testing. In what is known as concurrency, some low-rate initial production aircraft lots would be delivered in early block configurations and eventually upgraded to Block 3F once development is complete. After 17,000 flight test hours, the final flight for the SDD phase was completed in April 2018. Like the F-22, the F-35 has been targeted by cyber attacks and technology theft efforts, as well as potential vulnerabilities in the integrity of the supply chain. Testing found several major problems. Early F-35B airframes had premature cracking, the F-35C arrestor hook design was unreliable, fuel tanks were too vulnerable to lightning strikes, the helmet display had problems, and more. Software was repeatedly delayed due to its unprecedented scope and complexity. In 2009, the DoD Joint Estimate Team estimated that the program was 30 months behind the public schedule. In 2011, the program was rebaselined, that is, its cost and schedule goals were changed, pushing the IOC from the planned 2010 to July 2015. The decision to simultaneously test, fix defects, and begin production was criticized as inefficient. In 2014, Under-Secretary of Defense for Acquisition Frank Kendall called it acquisition malpractice. The three variants shared just 25% of their parts, far below the anticipated commonality of 70%. The program received considerable criticism for cost overruns and for the total projected lifetime cost, as well as quality management shortcomings by contractors. The JSF program was expected to cost about $200 billion for acquisition in base year 2002 when SDD was awarded in 2001. As early as 2005, the Government Accountability Office had identified major program risks in cost and schedule. The costly delays strained the relationship between the Pentagon and contractors. By 2017, delays and cost overruns had pushed the F-35 program's expected acquisition costs to $406.5 billion, with total lifetime cost to $1.5 trillion in then-year dollars, which also includes operations and maintenance. The unit cost of LRIP Lot 13 F-35A was $79.2 million. Delays in development and operational test and evaluation pushed full-rate production to 2023. Upgrades and further development. The first combat-capable Block 2B configuration, which had basic air-to-air and strike capabilities, was declared ready by the USMC in July 2015. The Block 3F configuration began operational test and evaluation in December 2018, the completion of which will conclude SDD. The F-35 program is also conducting sustainment and upgrade development, with early LRIP aircraft gradually upgraded to the baseline Block 3F standard by 2021. The F-35 is expected to be continually upgraded over its lifetime. The first upgrade program, called Continuous Capability Development and Delivery, began in 2019 and is currently planned to run to 2024. The near-term development priority of C2D2 is Block 4, which would integrate additional weapons, including those unique to international customers, refresh the avionics, improve ESM capabilities, and add remotely operated video-enhanced receiver support. C2D2 also places greater emphasis on agile software development to enable quicker releases. In 2018, the Air Force Life Cycle Management Center awarded contracts to General Electric and Pratt & Whitney to develop more powerful and efficient adaptive cycle engines for potential application in the F-35, leveraging the research done under the Adaptive Engine Transition Program. In 2022, the F-35 Adaptive Engine Replacement Program was launched to integrate adaptive cycle engines into the aircraft by 2028. Defense contractors have offered upgrades to the F-35 outside of official program contracts. In 2013, Northrop Grumman disclosed its development of a directional infrared countermeasures suite, named Threat Nullification Defensive Resource. The countermeasure system would share the same space as the distributed aperture system sensors and acts as a laser missile jammer to protect against infrared homing missiles. Israel wants more access to the core avionics to include their own equipment. In September 2022, the Pentagon refused to accept any more F-35s after determining Chinese-sourced materials were used in Honeywell pumps. Procurement and international participation. The United States is the primary customer and financial backer, with planned procurement of 1,763 F-35s for the U.S. Air Force, 353 F-35Bs, and 67 F-35Cs for the U.S. MC, and 273 F-35Cs for the USN. Additionally, the United Kingdom, Italy, the Netherlands, Turkey, Australia, Norway, Denmark, and Canada have agreed to contribute $4.375 billion towards development costs, with the United Kingdom contributing about 10% of the planned development costs as the sole Tier 1 partner. The initial plan was that the US and 8 major partner countries would acquire over 3,100 F-35s through 2035. The three tiers of international participation generally reflect financial stake in the program, the amount of technology transfer and subcontracts open for bid by national companies, and the order in which countries can obtain production aircraft. Alongside program partner countries, Israel and Singapore have joined as security cooperative participants. Sales to SCP and non-partner states, including Belgium, Japan, and South Korea, are made through the Pentagon's Foreign Military Sales Program. Turkey was removed from the F-35 program in July 2019 over security concerns following its purchase of a Russian S-400 surface-to-air missile system. Design. Overview. The F-35 is a family of single-engine, supersonic, stealth multirole fighters. The second fifth-generation fighter to enter U.S. service and the first operational supersonic STOFLOW stealth fighter, the F-35 emphasizes low observables, advanced avionics, and sensor fusion that enable a high level of situational awareness and long-range lethality. The U.S. Air Force considers the aircraft its primary strike fighter for conducting suppression of enemy air defense missions, owing to the advanced sensors and mission systems. The F-35 has a wingtail configuration with two vertical stabilizers canted for stealth. Flight control surfaces include leading-edge flaps, flap airons, rudders, and all-moving horizontal tails. Leading-edge root extensions also run forwards to the inlets. The relatively short 35-foot wingspan of the F-35A and F-35B is set by the requirement to fit inside USN amphibious assault ship parking areas and elevators. The F-35C's larger wing is more fuel efficient. The fixed diverterless supersonic inlets use a bumped compression surface and forward swept cowl to shed the boundary layer of the forebody away from the inlets, which form a viaduct for the engine. Structurally, the F-35 drew upon lessons from the F-22. Composites comprise 35% of airframe weight, with the majority being bismaleimide and composite epoxy materials as well as some carbon nanotube reinforced epoxy in later production lots. The F-35 is considerably heavier than the lightweight fighters it replaces, with the lightest variant having an empty weight of 29,300 pounds. Much of the weight can be attributed to the internal weapons bays and the extensive avionics carried. While lacking the raw performance of the larger twin-engine F-22, the F-35 has kinematics competitive with fourth-generation fighters such as the F-16 and F/A-18, especially with ordnance mounted because the F-35's internal weapons carriage eliminates parasitic drag from external stores. All variants have a top speed of Mach 1.6, attainable with full internal payload. The powerful F-135 engine gives good subsonic acceleration and energy, with supersonic dash in afterburner. The large stabilizers, leading-edge extensions and flaps, and canted rudders provide excellent high alpha characteristics, with a trimmed alpha of 50 degrees. Relaxed stability and fly-by-wire controls provide excellent handling qualities and departure resistance. Having over double the F-16's internal fuel, the F-35 has a considerably greater combat radius, while stealth also enables a more efficient mission flight profile. Sensors and avionics. The F-35's mission systems are among the most complex aspects of the aircraft. The avionics and sensor fusion are designed to enhance the pilot's situational awareness and command and control capabilities and facilitate network-centric warfare. Key sensors include the Northrop Grumman and /APG-81 active electronically scanned array radar, B systems and /ASQ-239 Barracuda electronic warfare system, Northrop Grumman /Raytheon and /AAQ-37 distributed aperture system, Lockheed Martin and /AAQ-40 electro-optical targeting system and Northrop Grumman and /ASQ-242 communications, navigation, and identification suite. The F-35 was designed with sensor intercommunication to provide a cohesive image of the local battlespace and availability for any possible use and combination with one another. For example, the APG-81 radar also acts as a part of the electronic warfare system. Much of the F-35's software was developed in C and C++ programming languages, while ADA-A3 code from the F-22 was also used. The Block 3F software has 8.6 million lines of code. The Green Hills Software Integrity Do 178B real-time operating system runs on integrated core processors. Data networking includes the IEEE 1394B and fiber channel buses. To enable fleet software upgrades for the software-defined radio systems and greater upgrade flexibility and affordability, the avionics leverage commercial off-the-shelf components when practical. The mission systems software, particularly for sensor fusion, was one of the program's most difficult parts and responsible for substantial program delays. The APG-81 radar uses electronic scanning for rapid beam agility and incorporates passive and active air-to-air modes, strike modes, and synthetic aperture radar capability, with multiple target track while scan at ranges in excess of 80 nmi. The antenna is tilted backwards for stealth. Complementing the radar is the AAQ-37 DOS, which consists of 6 infrared sensors that provide all-aspect missile launch warning and target tracking. The DOS acts as a situational awareness infrared search and track and gives the pilot spherical infrared and night vision imagery on the helmet visor. The ASQ-239 Barracuda electronic warfare system has 10 radio frequency antennas embedded into the edges of the wing and tail for all-aspect radar warning receiver. It also provides sensor fusion of radio frequency and infrared tracking functions, geolocation threat targeting, and multispectral image countermeasures for self-defense against missiles. The electronic warfare system is capable of detecting and jamming hostile radars. The AAQ-40 EOTS is mounted internally behind a faceted low observable window under the nose and performs laser targeting, forward-looking infrared, and long-range IRST functions. The ASQ-242 CNI suite uses a half-dozen different physical links, including the directional multi-function advanced data link, for covered CNI functions. Through sensor fusion, information from radio frequency receivers and infrared sensors are combined to form a single tactical picture for the pilot. The all-aspect target direction and identification can be shared via MADVL to other platforms without compromising low observability, while Link 16 is present for communication with legacy systems. The F-35 was designed from the outset to incorporate improved processors, sensors, and software enhancements over its lifespan. Technology Refresh 3, which includes a new core processor and a new cockpit display, is planned for Lot 15 aircraft. Lockheed Martin has offered the advanced EOTS for the Block 4 configuration. The improved sensor fits into the same area as the baseline EOTS with minimal changes. In June 2018, Lockheed Martin picked Raytheon for improved DOS. The U.S. Air Force has studied the potential for the F-35 to orchestrate attacks by unmanned combat aerial vehicles via its sensors and communications equipment. Stealth and signatures. Stealth is a key aspect of the F-35's design, and radar cross-section is minimized through careful shaping of the airframe and the use of radar-absorbent materials. Visible measures to reduce RCS include alignment of edges, serration of skin panels, and the masking of the engine face and turbine. Additionally, the F-35's diverterless supersonic inlet uses a compression bump and forward-swept cowl rather than a splitter gap or bleed system to divert the boundary layer away from the inlet duct, eliminating the diverter cavity and further reducing radar signature. The RCS of the F-35 has been characterized as lower than a metal golf ball at certain frequencies and angles. In some conditions, the F-35 compares favorably to the F-22 in stealth. For maintainability, the F-35's stealth design took lessons learned from prior stealth aircraft such as the F-22. The F-35's radar-absorbent fiber moskin is more durable and requires less maintenance than older top coats. The aircraft also has reduced infrared and visual signatures as well as strict controls of radio frequency emitters to prevent their detection. The F-35's stealth design is primarily focused on high-frequency X-band wavelengths. Low-frequency radars can spot stealthy aircraft due to Rayleigh scattering, but such radars are also conspicuous, susceptible to clutter, and lack precision. To disguise its RCS, the aircraft can mount 4 Lüneburg lens reflectors. Noise from the F-35 caused concerns in residential areas near potential bases for the aircraft, and residents near 2 such bases, Luke Air Force Base, Arizona, and Eglin Air Force Base, Florida, requested environmental impact studies in 2008 and 2009 respectively. Although the noise level in decibels were comparable to those of prior fighters such as the F-16, the sound power of the F-35 is stronger, particularly at lower frequencies. Subsequent surveys and studies have indicated that the noise of the F-35 was not perceptibly different from the F-16 and F/A-18E/F, though the greater low-frequency noise was noticeable for some observers. Cockpit. The glass cockpit was designed to give the pilot good situational awareness. The main display is a 20 by 8-inch panoramic touchscreen, which shows flight instruments, stores management, CNI information, and integrated caution and warnings. The pilot can customize the arrangement of the information. Below the main display is a smaller standby display. The cockpit has a speech recognition system developed by ADAS-L. The F-35 does not have a head-up display. Instead, flight and combat information is displayed on the visor of the pilot's helmet in a helmet-mounted display system. The one-piece tinted canopy is hinged at the front and has an internal frame for structural strength. The Martin-Baker US-16E ejection seat is launched by a twin catapult system housed on side rails. There is a right-hand side stick and throttle hands-on throttle and stick system. For life support, an onboard oxygen generation system is fitted and powered by the integrated power package, with an auxiliary oxygen bottle and backup oxygen system for emergencies. The Vision Systems International Helmet Display is a key piece of the F-35's human-machine interface. Instead of the head-up display mounted atop the dashboard of earlier fighters, the HMDS puts flight and combat information on the helmet visor, allowing the pilot to see it no matter which way they are facing. Infrared and night vision imagery from the distributed aperture system can be displayed directly on the HMDS and enables the pilot to see through the aircraft. The HMDS allows an F-35 pilot to fire missiles at targets even when the nose of the aircraft is pointing elsewhere by cueing missile seekers at high angles off bore sight. Each helmet costs $400,000. The HMDS weighs more than traditional helmets, and there is concern that it can endanger lightweight pilots during ejection. Due to the HMDS's vibration, jitter, night vision, and sensor display problems during development, Lockheed Martin and Elbit issued a draft specification in 2011 for an alternative HMDS based on the AN/AVS-9 night vision goggles as backup, with B systems chosen later that year. A cockpit redesign would be needed to adopt an alternative HMDS. Following progress on the baseline helmet, development on the alternative HMDS was halted in October 2013. In 2016, the Gen 3 helmet with improved night vision camera, new liquid crystal displays, automated alignment, and software enhancements was introduced with LRIP Lot 7. Armament. To preserve its stealth shaping, the F-35 has 2 internal weapons bays with 4 weapons stations. The 2 outboard weapon stations each can carry ordnance up to 2,500 pounds, or 1,500 pounds for the F-35B, while the 2 inboard stations carry air-to-air missiles. Air-to-surface weapons for the outboard station include the Joint Direct Attack Munition, Paveway series of bombs, Joint Standoff Weapon, and cluster munitions. The station can also carry multiple smaller munitions such as the GBU-39 small diameter bombs, GBU-53/BSDB-2, and Spear-3 anti-tank missiles. Up to 4 SDBs can be carried per station for the F-35A and F-35C, and 3 for the F-35B. The inboard station can carry the AIM-120 AMRAAM. 2 compartments behind the weapons base contain flares, chaff, and towed decoys. The aircraft can use 6 external weapons stations for missions that do not require stealth. The wingtip pylons each can carry an AIM-9X or AIM-132 SRAM and are canted outwards to reduce their radar cross-section. Additionally, each wing has a 5,000 pounds inboard station and a 2,500 pounds middle station, or 1,500 pounds for F-35B. The external wing stations can carry large air-to-surface weapons that would not fit inside the weapons bays such as the AGM-158 Joint Air-to-Surface Standoff Missile Cruise Missile. An air-to-air missile load of 8 AIM-120S and 2 AIM-9S is possible using internal and external weapons stations. A configuration of 6 2,000 pounds bombs, 2 AIM-120S, and 2 AIM-9S can also be arranged. The F-35A is armed with a 25mm GAU-22 rotary cannon mounted internally near the left wing root with 182 rounds carried. The gun is more effective against ground targets than the 20mm cannon carried by other U.S. Air Force fighters. The F-35B and F-35C have no internal gun and instead can use a Terma A/S multi-mission pod carrying the GAU-22/A and 220 rounds. The pod is mounted on the center line of the aircraft and shaped to reduce its radar cross-section. In lieu of the gun, the pod can also be used for different equipment and purposes, such as electronic warfare, aerial reconnaissance, or rear-facing tactical radar. Lockheed Martin is developing a weapon rack called Sidekick that would enable the internal outboard station to carry 2 AIM-120S, thus increasing the internal air-to-air payload to 6 missiles, currently offered for Block 4. Block 4 will also have a rearranged hydraulic line and bracket to allow the F-35B to carry 4 SDBs per internal outboard station. Integration of the MBDA Meteor is also planned. The U.S. Air Force and USN are planning to integrate the AGM-88G ARM-ER internally in the F-35A and F-35C. Norway and Australia are funding an adaptation of the Naval Strike Missile for the F-35, designated Joint Strike Missile. 2 missiles can be carried internally with an additional 4 externally. Nuclear weapons delivery via internal carriage of the B-61 nuclear bomb is planned for Block 4B in 2024. Both hypersonic missiles and direct energy weapons such as solid-state laser are currently being considered as future upgrades. Lockheed Martin is studying integrating a fiber laser that uses spectral beam combining multiple individual laser modules into a single high-power beam, which can be scaled to various levels. The U.S. Air Force plans for the F-35A to take up the close air support mission in contested environments, amid criticism that it is not as well suited as a dedicated attack platform. U.S. Air Force Chief of Staff Mark Welsh placed a focus on weapons for sorties, including guided rockets, fragmentation rockets that shatter into individual projectiles before impact, and more compact ammunition for higher capacity gun pods. Fragmentary rocket warheads create greater effects than cannon shells, as each rocket creates a 1,000-round burst, delivering more projectiles than a strafing run. Engine. The single-engine aircraft is powered by the Pratt & Whitney F135 low-bypass augmented turbofan with rated thrust of 43,000 lbf. Derived from the Pratt & Whitney F119 used by the F-22, the F135 has a larger fan and higher bypass ratio to increase subsonic thrust and fuel efficiency, and unlike the F119, is not optimized for supercruise. The engine contributes to the F-35's stealth by having a low observable augmenter, or afterburner, that incorporates fuel injectors into thick curved vanes. These vanes are covered by ceramic radar-absorbent materials and mask the turbine. The stealthy augmenter had problems with pressure pulsations, or screech, at low altitude and high speed early in its development. The low observable axisymmetric nozzle consists of 15 partially overlapping flaps that create a sawtooth pattern at the trailing edge, which reduces radar signature and creates shed vortices that reduce the infrared signature of the exhaust plume. Due to the engine's large dimensions, the USN had to modify its underway replenishment system to facilitate at-sea logistics support. The F-35's integrated power package performs power and thermal management and integrates environment control, auxiliary power unit, engine starting, and other functions into a single system. The F-135 PW600 variant for the F-35B incorporates the shaft-driven lift fan to allow stow-flow operations. Designed by Lockheed Martin and developed by Rolls-Royce, the SDLF, also known as the Rolls-Royce Lift System, consists of the lift fan, drive shaft, 2 roll posts, and a 3-bearing swivel module. The thrust vectoring 3BSM nozzle allows the main engine exhaust to be deflected downward at the tail of the aircraft and is moved by a fuel hydraulic actuator that uses pressurized fuel as the working fluid. Unlike the Harrier's Pegasus engine that entirely uses direct engine thrust for lift, the F-35B's system augments the swivel nozzle's thrust with the lift fan. The fan is powered by the low-pressure turbine through a drive shaft when engaged with a clutch and placed near the front of the aircraft to provide a counterbalancing thrust. Roll control during slow flight is achieved by diverting unheated engine bypass air through wing-mounted thrust nozzles called roll posts. An alternative engine, the General Electric/Rolls-Royce F136, was being developed in the 2000s. Originally, F-35 engines from Lot 6 onward were competitively tendered. Using technology from the General Electric YF-120, the F-136 was claimed to have a greater temperature margin than the F-135 due to the higher mass flow design making full use of the inlet. The F-136 was cancelled in December 2011 due to lack of funding. The F-35 is expected to receive propulsion upgrades over its life cycle to adapt to emerging threats and enable additional capabilities. In 2016, the Adaptive Engine Transition Program was launched to develop and test adaptive cycle engines, with one major potential application being the re-engining of the F-35. In 2018, both GE and P&W were awarded contracts to develop 45,000 lbf thrust class demonstrators, with the designations XA100 and XA101 respectively. In addition to potential re-engining, P&W also plans to improve the baseline F135. In 2017, P&W announced the F135 Growth Option 1.0 and 2.0, Growth Option 1.0 was a drop power module upgrade that offered 6-10% thrust improvement and 5-6% fuel burn reduction, while Growth Option 2.0 would be the adaptive cycle XA101. In 2020, P&W shifted its F-135 upgrade plan from the growth options to a series of engine enhancement packages along with some additional capabilities, while the XA101 became a separate clean sheet design. The capability packages are planned to be incorporated in 2-year increments starting in the mid-2020s. In December of 2020, GE's XA100 completed its first successful run. GE's detailed design was completed in February 2019, and initial testing at GE's high-altitude test facility in Avondale, Ohio was concluded in May 2021. GE expects that the A100 can enter service with the F-35A and C in 2027 at the earliest. Maintenance and logistics. The F-35 is designed to require less maintenance than prior stealth aircraft. Some 95% of all field replaceable parts are one deep, that is, nothing else need be removed to reach the desired part. For instance, the ejection seat can be replaced without removing the canopy. The F-35 has a fiber radar absorbent material baked into the skin, which is more durable, easier to work with, and faster to cure than older RAM coatings. Similar coatings are being considered for application on older stealth aircraft such as the F-22. Skin corrosion on the F-22 led the F-35 using a less galvanic corrosion-inducing skin gap filler, fewer gaps in the airframe skin needing filler, and better drainage. The flight control system uses electro-hydrostatic actuators rather than traditional hydraulic systems. These controls can be powered by lithium-ion batteries in case of emergency. Commonality between variants led to the USMC's first aircraft maintenance field training detachment, which applied U.S. Air Force lessons to their F-35 operations. The F-35 was initially supported by a computerized maintenance management system named Autonomic Logistics Information System. In concept, any F-35 can be serviced at any maintenance facility and all parts can be globally tracked and shared as needed. Due to numerous problems, such as unreliable diagnoses, excessive connectivity requirements, and security vulnerabilities, ALICE is being replaced by the cloud-based Operational Data Integrated Network. From September 2020, Odin base kits were running ALICE software, as well as Odin software, first at Marine Corps Air Station Yuma, Arizona, then at Naval Air Station Lemoore, California, in support of Strike Fighter Squadron 125 on July 16, 2021, and then Nellis Air Force Base, Nevada, in support of the 422nd Test and Evaluation Squadron on August 6, 2021. In 2022, over a dozen more OBK sites will replace the ALICE's Standard Operating Unit unclassified servers. OBK performance is double that of ALICE. Operational history. Testing. The first F-35A, AA-1, conducted its engine run in September 2006 and first flew on December 15, 2006. Unlike all subsequent aircraft, AA-1 did not have the weight optimization from SWAT, consequently, it mainly tested subsystems common to subsequent aircraft, such as the propulsion, electrical system, and cockpit displays. This aircraft was retired from flight testing in December 2009 and was used for live-fire testing at NAS China Lake. The first F-35B, BF-1, flew on June 11, 2008, while the first weight-optimized F-35A and F-35C, AF-1 and CF-1, flew on November 14, 2009 and June 6, 2010 respectively. The F-35B's first hover was on March 17, 2010, followed by its first vertical landing the next day. The F-35 Integrated Test Force consisted of 18 aircraft at Edwards Air Force Base and Naval Air Station Patuxent River. 9 aircraft at Edwards, 5 F-35s, 3 F-35Bs, and 1 F-35C, performed flight sciences testing such as F-35A envelope expansion, flight loads, stores separation, as well as mission systems testing. The other 9 aircraft at Patuxent River, 5 F-35Bs and 4 F-35Cs, were responsible for F-35B and C envelope expansion and STOFLO and CV suitability testing. Additional carrier suitability testing was conducted at Naval Air Warfare Center Aircraft Division at Lakehurst, New Jersey. 2 non-flying aircraft of each variant were used to test static loads and fatigue. For testing avionics and mission systems, a modified Boeing 737-300 with a duplication of the cockpit, the Lockheed Martin Catbird, has been used. Field testing of the F-35's sensors were conducted during Exercise Northern Edge 2009 and 2011, serving as significant risk reduction steps. Flight tests revealed several serious deficiencies that required costly redesigns, caused delays, and resulted in several fleet-wide groundings. In 2011, the F-35C failed to catch the arresting wire in all 8 landing tests. A redesigned tailhook was delivered 2 years later. By June 2009, many of the initial flight test targets had been accomplished, but the program was behind schedule. Software and mission systems were among the biggest sources of delays for the program, with sensor fusion proving especially challenging. In fatigue testing, the F-35B suffered several premature cracks, requiring a redesign of the structure. A third non-flying F-35B is currently planned to test the redesigned structure. The F-35B and C also had problems with the horizontal tails, suffering heat damage from prolonged afterburner use. Early flight control laws had problems with wing drop and also made the airplane sluggish, with high angles of attack tests in 2015 against an F-16 showing a lack of energy. At-sea testing of the F-35B was first conducted aboard USS Wasp. In October 2011, 2 F-35Bs conducted 3 weeks of initial sea trials, called Development Test I. The second F-35B trials, Development Test 2, began in August 2013, with tests including nighttime operations. 2 aircraft completed 19 nighttime vertical landings using DOS imagery. The first operational testing involving 6 F-35Bs was done on the Wasp in May 2015. The final Development Test 3 on USS America involving operations in high sea states was completed in late 2016. A Royal Navy F-35 conducted the first rolling landing on board HMS Queen Elizabeth in October 2018. After the redesigned tailhook arrived, the F-35C's carrier-based development test I began in November 2014 aboard USS Nimitz and focused on basic day carrier operations and establishing launch and recovery handling procedures. Development Test 2, which focused on night operations, weapons loading, and full power launches, took place in October 2015. The final Development Test 3 was completed in August 2016, and included tests of asymmetric loads and certifying systems for landing qualifications and interoperability. Operational test of the F-35C began in 2018. The F-35's reliability and availability have fallen short of requirements, especially in the early years of testing. The Alice maintenance and logistics system was plagued by excessive connectivity requirements and faulty diagnoses. In late 2017, the GA reported the time needed to repair an F-35 part averaged 172 days, which was twice the program's objective, and that shortage of spare parts was degrading readiness. In 2019, while individual F-35 units have achieved mission-capable rates of over the target of 80% for short periods during deployed operations, fleet-wide rates remained below target. The fleet availability goal of 65% was also not met, although the trend shows improvement. Gun accuracy of the F-35A remains unacceptable. As of 2020, the number of the program's most serious issues have been decreased by half. Operational test and evaluation with Block 3F, the final configuration for SDD, began in December 2018. United States. Training. U.S. Marine Corps, U.S. Air Force, U.S. Navy, United Kingdom. The United Kingdom's Royal Air Force and Royal Navy both operate the F-35B, known simply as the Lightning in British service. It has replaced the Harrier GR9, which was retired in 2010, and Tornado GR4, which was retired in 2019. The F-35 is to be Britain's primary strike aircraft for the next 3 decades. One of the Royal Navy's requirements for the F-35B was a shipborne rolling and vertical landing mode to increase maximum landing weight by using wing lift during landing. When operating on the aircraft carriers HMS Queen Elizabeth and HMS Prince of Wales, British F-35Bs use ski jumps. The Italian Navy used the same process. British F-35Bs are not intended to use the Brimstone 2 missile. In July 2013, Chief of the Air Staff, Air Chief Marshal Sir Stephen Dalton announced that No. 617 Squadron would be the RAF's first operational F-35 squadron. The second operational squadron will be the Fleet Air Arm's 809 Naval Air Squadron, which will stand up in April 2023 or later. No. 17 Test and Evaluation Squadron stood up on April 12, 2013 as the operational evaluation unit for the Lightning, becoming the first British squadron to operate the type. By June 2013, the RAF had received 3 F-35s of the 48 on order, initially based at Eglin Air Force Base. In June 2015, the F-35B undertook its first launch from a ski jump at NAS Patuxent River. On July 5, 2017, it was announced the second UK-based RAF squadron would be No. 207 Squadron, which reformed on August 1, 2019 as the Lightning Operational Conversion Unit. No. 617 Squadron reformed on April 18, 2018 during a ceremony in Washington, D.C., becoming the first RAF frontline squadron to operate the type, receiving its first 4 F-35Bs on June 6, flying from MCAS Beaufort to RAF Marham. On January 10, 2019, No. 617 Squadron and its F-35s were declared combat-ready. In April 2019, No. 617 Squadron deployed to RAF Akrotiri, Cyprus, the type's first overseas deployment. On June 25, 2019, the first combat use of an RAF F-35B was reportedly undertaken as armed reconnaissance flights searching for Islamic State targets in Iraq and Syria. In October 2019, the Dambusters and No. 17 TES F-35s were embarked on HMS Queen Elizabeth for the first time. No. 617 Squadron departed RAF Marham on January 22, 2020 for their first exercise Red Flag with the Lightning. Australia. Australia's first F-35, designated A35-001, was manufactured in 2014, with flight training provided through International Pilot Training Center at Luke Air Force Base in Arizona. The first 2 F-35s were unveiled to the Australian public on March 3, 2017 at the Avalon Airshow. By 2021, the Royal Australian Air Force had accepted 26 F-35s, with 9 in the U.S. and 17 operating at No. 3 Squadron and No. 2 Operational Conversion Unit at RAF Base Williamtown. With 41 trained RAF pilots and 225 trained technicians for maintenance, the fleet was declared ready to deploy on operations. It is expected that Australia will receive all 72 F-35s by 2023. Israel. The Israeli Air Force declared the F-35 operationally capable on December 6, 2017. According to Kuwaiti newspaper Al Jarida, in July 2018, a test mission of at least 3 IAF F-35s flew to Iran's capital Tehran and back from Tel Aviv. While publicly unconfirmed, regional leaders acted on the report. Iran's supreme leader Ali Khamenei reportedly fired the Air Force chief and commander of Iran's Revolutionary Guard Corps over the mission. On May 22, 2018, IAF Chief Amikam Norkin said that the service had employed their F-35s in 2 attacks on 2 battlefronts, marking the first combat operation of an F-35 by any country. Norkin said it had been flown all over the Middle East, and showed photos of an F-35I flying over Beirut in daylight. In July 2019, Israel expanded its strikes against Iranian missile shipments. IAF F-35 is allegedly struck Iranian targets in Iraq twice. In November 2020, the IAF announced the delivery of an F-35I testbed aircraft amongst a delivery of 4 aircraft received in August. This example will be used to test and integrate Israeli-produced weapons and electronic systems on future F-35s received. This is the only example of a testbed F-35 delivered to an air force outside of the United States. On May 11, 2021, 8 IAF F-35s took part in an attack on 150 targets in Hamas rocket array, including 50-70 launch pits in the northern Gaza Strip, as part of Operation Guardian of the Walls. On March 6, 2022, the IDF stated that on March 15, 2021 F-35s shot down 2 Iranian drones carrying weapons to the Gaza Strip. This was the first operational shoot-down and interception carried out by the F-35. Italy. Italy's F-35s were declared to have reached initial operational capability on November 30, 2018. At the time, Italy had taken delivery of 10 F-35s and 1 F-35B, with 2 F-35s and the 1 F-35B being stationed in the U.S. for training. The remaining 8 F-35s were stationed in Amendola. Japan. Japan's F-35s were declared to have reached initial operational capability on March 29, 2019. At the time, Japan had taken delivery of 10 F-35s stationed in Misawa Air Base. Japan plans to eventually acquire a total of 147 F-35s, which will include 42 F-35Bs. It plans to use the latter variant to equip Japan's Izumo-class multi-purpose destroyer. Norway. On November 6, 2019, Norway declared initial operational capability for its fleet of 15 F-35s out of a planned 52 F-35s. On January 6, 2022, Norway's F-35s replaced its F-16s for the NATO Quick Reaction Alert mission in the High North. Netherlands. On December 27, 2021, the Netherlands declared initial operational capability for its fleet of 24 F-35s that it has received to date from its order for 46 F-35s. In 2022, the Netherlands announced they will order an additional 6 F-35s, totaling 52 aircraft ordered. Variants. The F-35 was designed with 3 initial variants: the F-35A, a CTOL land-based version, the F-35B, a STOFLOW version capable of use either on land or on aircraft carriers, and the F-35C, a CATOBAR carrier-based version. Since then, there has been work on the design of nationally specific versions for Israel and Canada, as well as initial concept design work for an updated version of the F-35A, which would become the F-35D. F-35A. The F-35A is the conventional takeoff and landing variant intended for the U.S. Air Force and other air forces. It is the smallest, lightest version and capable of 9 grams, the highest of all variants. Although the F-35A currently conducts aerial refueling via boom and receptacle method, the aircraft can be modified for probe and drogue refueling if needed by the customer. A drag chute pod can be installed on the F-35A, with the Royal Norwegian Air Force being the first operator to adopt it. F-35B. The F-35B is the short takeoff and vertical landing variant of the aircraft. Similar in size to the A variant, the B sacrifices about a third of the A variant's fuel volume to accommodate the SDLF. This variant is limited to 7 grams. Unlike other variants, the F-35B has no landing hook. The stowflow/hook control instead engages conversion between normal and vertical flight. The F-35B can also perform vertical and/or short takeoff and landing. F-35C. The F-35C variant is designed for catapult-assisted takeoff but arrested recovery operations from aircraft carriers. Compared to the F-35A, the F-35C features larger wings with foldable wingtip sections, larger control surfaces for improved low-speed control, stronger landing gear for the stresses of carrier-arrested landings, a twin-wheel nose gear, and a stronger tailhook for use with carrier arrestor cables. The larger wing area allows for decreased landing speed while increasing both range and payload. The F-35C is limited to 7.5 grams. F-35IADIR. The F-35IADIR is an F-35A with unique Israeli modifications. The U.S. initially refused to allow such changes before permitting Israel to integrate its own electronic warfare systems, including sensors and countermeasures. The main computer has a plug-and-play function for add-on systems. Proposals include an external jamming pod, and new Israeli air-to-air missiles and guided bombs in the internal weapon bays. A senior IAF official said that the F-35's stealth may be partly overcome within 10 years despite a 30 to 40-year service life, thus Israel's insistence on using their own electronic warfare systems. Israel Aerospace Industries has considered a 2-seat F-35 concept, an IAI executive noted. There is a known demand for 2 seats not only from Israel but from other air forces. IAI plans to produce conformal fuel tanks. Proposed variants: CF-35. New export variant. F-35D. Operators: Australia. Royal Australian Air Force 50 F-35A delivered as of July 2022, of 72 ordered. Belgian Air Component 34 F-35A planned. Denmark Royal Danish Air Force 6 F-35A delivered of the 27 planned. Finland Finnish Air Force F-35A Block 4 selected Viaduct the HX fighter program to replace the current F/A-18 Hornets, with 64 F-35s on order. German Air Force 35 F-35A ordered. Israeli Air Force 33 delivered as of March 2022. Includes 1 F-35 testbed aircraft for indigenous Israeli weapons, electronics, and structural upgrades, designated. A total of 50 ordered. Italian Air Force 12 F-35s and 1 F-35B delivered as of 2020, with Italy planning to order 60 F-35s and 15 F-35Bs for the Italian Air Force. Italian Navy 2 had been delivered as of October 2020 with 15 F-35Bs planned for the Italian Navy. Japan Air Self-Defense Force 23 F-35 is operational as of December 2021 with a total order of 147, including 105 F-35s and 42 F-35Bs. Netherlands Royal Netherlands Air Force 24 F-35 is delivered and operational out of 37 ordered. 52 F-35 as planned in total. Norway Royal Norwegian Air Force 31 F-35 as delivered and operational, of which 21 are in Norway and 10 are based in the US for training as of August 11, 2021 of 52 F-35 as planned in total. They differ from other F-35A through the addition of a drogue parachute. Poland Polish Air Force 32 F-35 as on order. Plans for 2 more squadrons consisting of 16 jets each, for a total of 32 additional F-35s. South Korea Republic of Korea Air Force 40 F-35 as ordered and delivered as of January 2022, with 20 more F-35 as planned. Republic of Korea Navy about 20 F-35Bs planned. It has not yet been approved by South Korean Parliament. Singapore Republic of Singapore Air Force 4 F-35Bs to be ordered with option to order 8 more as of March 2019. Switzerland Swiss Air Force 36 F-35A ordered to replace the current F-5E/F Tiger II and F/A-18C/D Hornet. Deliveries will begin in 2027 and conclude in 2030. United Kingdom Royal Air Force and Royal Navy 27 F-35Bs received with 23 in the UK after the loss of 1 aircraft in November 2021, the other 3 are in the US where they are used for testing and training. 42 to be fast-tracked by 2023, a total of 48 ordered as of 2021, a total of 138 were originally planned. The expectation in 2021 was to eventually reach around 60 or 80. United States Air Force 302 delivered with 1,763 F-35 as planned. United States Marine Corps 114 F-35B/C delivered with 353 F-35Bs and 67 F-35Cs planned. United States Navy 26 delivered with 273 F-35Cs planned. Order and approval cancellations. Turkish Air Force 4 F-35 as delivered to Luke Air Force Base for training in July 2018. 30 were ordered, of up to 100 total planned. Future purchases have been banned by the US with contracts cancelled by early 2020. All 4 F-35s have been withheld at Luke Air Force Base and not sent to Turkey. On July 20, 2020, the U.S. government formally approved the seizure of 8 F-35 as originally bound for Turkey and transferred them to the U.S. Air Force, together with a contract to modify them to U.S. Air Force specifications. As of 2022, the U.S. has not refunded the $1.4 billion payment made by Turkey for purchasing the F-35A fighters. United Arab Emirates Air Force, up to 50 F-35 as planned. But on January 27, 2021, the Biden administration temporarily suspended the F-35 sales to the UAE. After pausing the bill to review the sale, the Biden administration confirmed to move forward with the deal on April 13, 2021. In December 2021, UAE withdrew from purchase F-35s for reasons not to agree to the additional terms of the transaction on the part of the USA. Accidents and notable incidents. On June 23, 2014, an F-35A's engine caught fire at Eglin AFB. The pilot escaped unharmed, while the aircraft sustained an estimated $50 million in damage. The accident caused all flights to be halted on July 3. The fleet returned to flight on July 15 with flight envelope restrictions. In June 2015, the U.S. Air Force Air Education and Training Command issued its official report, which blamed the failure on the third-stage rotor of the engine's fan module, pieces of which cut through the fan case and upper fuselage. Pratt & Whitney applied an extended rub-in to increase the gap between the second stator and the third rotor integral arm seal, as well as design alterations to pre-trench the stator by early 2016. On September 28, 2018, the first crash occurred involving a USMC F-35B near Marine Corps Air Station Beaufort, South Carolina. The pilot ejected safely. The crash was attributed to a faulty fuel tube. All F-35s were grounded on October 11 pending a fleet-wide inspection of the tubes. The next day, most U.S. Air Force and USN F-35s returned to flight status following the inspection. On April 9, 2019, a JASTF F-35A attached to Misawa Air Base disappeared from radar about 84 miles east of the Aomori Prefecture during a training mission over the Pacific Ocean. The pilot, Major Akinori Hosamai, had radioed his intention to abort the drill before disappearing. The U.S. and Japanese navies searched for the missing aircraft and pilot, finding debris on the water that confirmed its crash. Hosamai's remains were recovered in June. In response, Japan grounded its 12 F-35s. There was speculation that China or Russia might attempt to salvage it. The Japanese Defense Ministry announced there had been no reported activities from either country. The F-35 reportedly did not send a distress signal, nor did the pilot attempt any recovery maneuvers as it descended at a rapid rate. The accident report attributed the cause to the pilot's spatial disorientation. On May 19, 2020, a U.S. Air Force F-35A from the 58th Fighter Squadron crashed while landing at Eglin AFB. The pilot ejected and was in stable condition. The accident was attributed to a combination of pilot error induced by fatigue, a design issue with the oxygen system and the aircraft's more complex nature being distracting, as well as a malfunctioning head-mounted display and an unresponsive flight control system. On September 29, 2020, a USMC F-35B crashed in Imperial County, California, after colliding with a Marine Corps KC-130 during air-to-air refueling. The F-35B pilot was injured in the ejection, and the KC-130 crash-landed gear up in a field. On March 12, 2021, during a close air support weapons training nighttime flight near Marine Corps Air Station Yuma, Arizona, a round fired from the belly-mounted gun pod on a F-35B, a 25 mm Gauss/A Gatling gun, detonated shortly after leaving the barrel of the gun. This specific round fired was a PGU-32/BSAPHEIT, which is designed to detonate after the round has penetrated the target's armor, beginning a fuse-delayed explosion and then spread the incendiary material. These rounds are also equipped with graze detection, meaning even with a slight grazing blow to a target they will explode and spread the incendiary substance. The mishap was classified as a Class C, meaning the damage incurred a cost of between $60,000 to $600,000 to repair, and/or a non-fatal injury forcing lost time from work for the remainder of the working day that the injury occurred. The aircraft itself was grounded for maintenance for over 3 months, but the pilot was uninjured. The shrapnel from the round penetrated several parts of the aircraft, requiring their replacement. On November 17, 2021, a Royal Air Force F-35B crashed during routine operations in the Mediterranean. The pilot was safely recovered to HMS Queen Elizabeth. Early reports suggested some of the covers and engine blanks had not been removed before takeoff. The wreckage, including all security-sensitive equipment, was largely recovered with the assistance of U.S. and Italian forces. On January 4, 2022, a South Korean Air Force F-35A made a belly landing after all systems failed except the flight controls and the engine. The pilot heard a series of bangs during low-altitude flight, and various systems stopped working. The control tower suggested that the pilot eject, but he managed to land the plane without deploying the landing gear, walking away uninjured. On January 24, 2022, a USN F-35C with VFA-147 suffered a ramp strike while landing on the USS Carl Vinson and was lost overboard in the South China Sea, injuring 7 crew members. The pilot ejected safely and was recovered from the water. On March 2, 2022, the aircraft was recovered from a depth of approximately 12,400 feet with the aid of a remotely operated vehicle. On October 19, 2022, an F-35A crashed at the north end of the runway at Hill Air Force Base, Utah. The pilot safely ejected and was unharmed. The cause of the crash is under investigation. Specifications. Data from Lockheed Martin, F-35 specifications, Lockheed Martin, F-35 weaponry, Lockheed Martin, F-35 program status, F-35 program brief, FY 2019 Select Acquisition Report, Director of Operational Test and Evaluation. General characteristics. Crew, 1. Length, 51.4 feet. Wingspan, 35 feet. Height, 14.4 feet. Wing area, 460 square feet. Aspect ratio, 2.66. Empty weight, 29,300 pounds. Gross weight, 49,540 pounds. Max takeoff weight, 70,000 pounds. Fuel capacity, 18,250 pounds internal. Power plant, 1 times Pratt & Whitney F135 PW100 afterburning turbofan, 28,000 lbf thrust dry, 43,000 lbf with afterburner performance. Maximum speed, Mach 1.6 at altitude. Range, 1,500 nmi. Combat range, 669 nmi on internal fuel. 760 nmi interdiction mission on internal fuel, for internal air-to-air configuration. Service ceiling, 50,000 feet. G limits, plus 9.0. Wing loading, 107.7 lb/sq foot at gross weight. Thrust/weight, 0.87 at gross weight. Armament. Guns, 1 times 25 mm Gauss 22/A4 barrel rotary cannon, 180 rounds. Hardpoints, 4 times internal stations, 6 times external stations on wings with a capacity of 5,700 pounds internal, 15,000 pounds external, 18,000 pounds total weapons payload, with provisions to carry combinations of missiles, air-to-air missiles. AIM-120 AMRAAM, AIM-9X Sidewinder, AIM-132 ASRAAM, MBDA Meteor. Air-to-surface missiles. AGM-88 GRM-ER, AGM-158 JAS. Spear-3. Joint air-to-ground missile. Air-to-surface/anti-ship missiles. Joint strike missile. Anti-ship missiles. AGM-158 SEALRASM. Bombs, Joint Direct Attack Munition Series. Paveway Series Laser-Guided Bombs. Precision-Guided Glide Bomb. AGM-154 JSOW. GBU-39 Small Diameter Bomb. GBU-53/B Stormbreaker. B-61 Mod 12 Nuclear Bomb Avionics. AN/APG-81 AESA Radar. AN/AAQ-40E/O Targeting System. AN/AAQ-37 Distributed Aperture System Missile Warning System. AN/ASQ-239 Barracuda Electronic Warfare System. AN/ASQ-242 CNI Suite, which includes Harris Corporation Multi-Function Advanced Data Link Communication System. Link 16 Data Link. SINCARS. An IFF Interrogator and Transponder. Half-Quick. AM, VHF, UHF AM, and UHF FM radio. Guard Survival Radio. A radar altimeter. An instrument landing system. A TACAN system. Instrument carrier landing system. AJ-PALS. TADILJJVMF/VMF. Differences between variants. Appearances in media. See also. Related development. Lockheed Martin X-35 concept demonstrator aircraft for Joint Strike Fighter program, aircraft of comparable role, configuration, and era. Chengdu J-20 Chinese 5th generation fighter aircraft. HAL AMCA Indian 5th generation fighter under development by Hindustan Aeronautics Limited. Kai KF-21 Bormi advanced multirole fighter aircraft under development by South Korea and Indonesia. Lockheed Martin F-22 Raptor American 5th generation air superiority fighter. Shenyang FC-31 5th generation jet fighter under development by Shenyang Aircraft Corporation. Sukhoi Su-57 Russian 5th generation fighter aircraft. TAI TFX Turkish 5th generation fighter under development by Turkish Aerospace Industries. Sukhoi Su-75 Checkmate Russian single-engine 5th generation fighter under development by Sukhoi. Related lists. List of fighter aircraft. List of active United States military aircraft. List of mega projects, aerospace. Notes.